So far we have considered one group at a time, but now let's consider two groups at a time. Let's say S and T. So in order to understand one group, it may be helpful if we uh, consider another group and also mapping between the groups. Okay, and when we consider a mapping between two groups, just a simple mapping may not be very informative, but the mapping may be very useful if it conserves the structure of the group S to the structure of group T. And that kind of structure preserving mapping is called a homomorphism. So this word is made of two parts, homo and morph and ism, actually. Homo means the same in Greek, and morph means the shape or structure. So basically, this is a mapping that conserves the structure of a group. Okay? And more specifically, when we say structure preserving, what we mean is the following. Let's define homomorphism. So let's say we have two groups, S and T, and okay, not just groups. Let's consider semigroups, S and T. Groups are semigroups also. So let's say S and T are semigroups. So that means they are not just sets, but they have a binary operation. So each of them has a binary operation defined that obeys some rules of axioms of semigroups. Okay, and we consider a mapping from S to T. Okay, but it's not just a mapping. So mapping makes the correspondence between each element of S to an element of T. But not just that, we also impose the following condition. So if X and Y are elements of S, then f of xy is f of x times f of y. Okay? And of course, this is an element of T. So if this holds, then we say f is a homomorphism. Okay, so be careful. Here xy means the binary operation, multiplication between x and y within S. Okay, on the right hand side, the multiplication between f of x and f of y is the multiplication within the semigroup T. Okay, so these multiplications have different meanings. Okay, so this part and this multiplication, so they have different meaning. One is within S, one is within T. So in this sense, the multiplication in S is preserved as a multiplication in T. So in this sense, this mapping preserves the structure of the semigroup S into the semigroup T. So any monoid and a group is also a semigroup. You know, monoid is just a semigroup with the identity element, and a group is a semigroup with the identity element and inverse elements. So this definition of homomorphism also applies to monoids and groups. So now we know that by definition, a homomorphism preserves the multiplication in S and to T. But there are more that is preserved by a homomorphism, as we can see in the following lemma. Okay, so S and T are semigroups again. And let F be so F is a homomorphism from S to T. So if we say F is a homomorphism, that means this F preserves the multiplication in S to multiplication in T. Then F of S, so that means the image of S by F, so this is a set, so this is a subset of T. So this is a semigroup. Okay. And what this really means is it is semigroup, that is a subset of T, which is a semigroup. So we should call it sub-semigroup of T. So what is preserved is not only the multiplication, but also the structure as a semigroup as a whole. So let's prove this. So we want to show that F of S is a semigroup. Okay, this is what we need to show. So in order to show a set is a semigroup, then what we need to show is that the multiplication within this set is closed. I mean, this set is closed under multiplication, and also the multiplication is associative. Okay, so first let A and B be elements of F of S. Okay, so let's visualize this as this. So if we have S, if we have T, this image of F is a subset of T, like this. Okay, so the entire S is mapped to a subset of T, so which may coincide with T itself, but in general it is a proper subset of T. So let's pick two elements from this subset. So this is F of S. Okay. Then there exists X and Y in S such that A is equal to F of X and B is equal to F of Y. Right? So if we pick any two elements from this F of S, then there should be a corresponding elements in the semigroup S. Okay, let's B and let's see A. So to see this set is closed under multiplication, let's say take the product between A and B. Then that is F of X times F of Y, but F is supposed to be a homomorphism, so the product is conserved. So that becomes F of XY, which is of course an element of F of S. Therefore this set is, therefore F of S is closed under multiplication. And also we need to check that the multiplication is associative, but since T is a semigroup, the multiplication within F of S is also associative. Okay, is a semigroup. the multiplication in f of s, which is a subset of t, is also associative. So, therefore, f of s is a semigroup. And we are done. Now let's see the following theorem. This time we consider groups. So let's say G and H are groups, and a homomorphism F from G to H. So this is a homomorphism. So these are our assumptions. Then we have the following. First, if EG is let's say EG and EH are the identities of G and H respectively. You know, G and H are different groups, so they have different identity elements. Okay, then we have f of EG is equal to EH. So this means the identity element in G is mapped to the identity element of H by the homomorphism F. And second, for all x in G, we have the inverse element of f of x in H is equal to f of x inverse. Okay, so this is the inverse element of f of x. So x inverse is, of course, the inverse element of x in G. Okay, so that means the inverse element is mapped to an inverse element in H. And 3, f of G is a subgroup of H. So this is similar to the previous lemma. In the lemma it was sub-semigroup, but here it is stronger. So since G is a group and H is a group, in this case f of G is a subgroup of H. And 4, let us define a subset K, which is the elements of G such that that is mapped to the identity element of H. Okay, so all the elements of G that are mapped to the identity element of H. You know, since this homomorphism F may not be injective, potentially many elements of G may be mapped to the same identity element in H. Okay, so in that case, the number of elements in K may be greater than 1. But anyway, if we define this set K, then K is a normal subgroup group of G. Okay, K is a subset of G, of course. So between two groups and homomorphism, with the homomorphism, we have these 4 results. So let's prove this. First, let's prove this first point. So f of eg times f of eg. Since f is a homomorphism, we have f of eg times eg. But since eg is the identity element in G, we have eg here. Okay, and then, okay, this is of course an element in H, and every element in H, since H is a group, we have the inverse element of this. So by multiplying both sides by the inverse element of this, we have, let's say, by multiplying by f of eg inverse, then we have f of eg times f of eg, f of eg inverse times f of eg, f of eg inverse. But this is equal to the identity element of H, and this part becomes the identity element of EH. But since this is identity element, we have f of EG is equal to EH. So here it is. And next, we prove the inverse element of f of x is f of x inverse. So to show this, let's see. F of x inverse times f of x. Since f is a homomorphism, we have f of x inverse times x. But x inverse is of course the inverse element of x, so we have f of e g here. But as we know from the first part, this is equal to EH, which is the identity element of EH. So by multiplying both sides by fx inverse, then we have f of x inverse is equal to fx inverse. And we are done. And the third point is that f of g is a subgroup of H. So by lemma, by the previous lemma, f of g is a semigroup. So we only need to show the existence of the identity element within this subset, and also the existence of inverse element for every element in this subset. So of course, by part 1, we have this. We have this. So EH is the identity element of H is the image of the identity element of G, which is of course an element of f of g. Therefore, the identity element exists. And next, let A be any element from this image. Then there exists some element in G such that A is equal to f of x. And now A inverse is equal to f of x inverse. But from the previous part 2, we have this is equal to f of x inverse. Okay, so which is an element of the image. So therefore, every element within this subset, there exists an inverse element of that element within the same subset. Therefore, all the axioms of the group are satisfied. Therefore, f of g is a group. And next, let's prove part 4. That is, the subset defined by this is a normal subgroup of G. Okay, so let's write the definition again. So this is a subset of G that is mapped to the identity element of H by the homomorphism F. Okay, so to show that this is a normal subgroup, first we need to show that this is a subgroup. Okay, so let's say, let's see. So to show this is a subgroup, first we need to show that this K, subset K, is not empty. Okay, but it's easy to show. Since f of EG is equal to EH, at least the identity element of G belongs to this subset K. Therefore, K is not empty. Okay, and next, let x and y be elements of K. Then f of x is equal to f of y is equal to EH. That's the definition of K. So any element in K is mapped to the identity element of H. Okay, so we need to show that K is closed under multiplication. So we need to show that xy is an element of K. So this is what we need to show. Okay, so to show this, let's map xy by f. Then, since f is a homomorphism, this is f of x times f of y. Okay, but since x and y are both elements of K, they are both mapped to the identity element of H. But this is identity element of H. Therefore, x, y belongs to K. Therefore, closure condition is satisfied. Okay, and next, the existence of the identity element that is already shown here. So the identity element belongs to K, so that is okay. And the next is the inverse element of every element. So f of x inverse is fx inverse, but f of x is EH, the identity element of H. Of course, we are assuming x is an element of K. Okay, but the identity element of EH is EH, of course. Therefore, x inverse belongs to K. Therefore, every element of K has its inverse within K. Therefore, K is a subgroup of G. Now, next we need to show that this subgroup is normal. Okay, what is a normal subgroup, by the way? You should recall the definition. So we need to show that K is normal. So that means, by definition, for all elements in G, we have x inverse and for all element A in K, we have X inverse A, X is an element of K. So if we can show this, then we prove that K is a normal subgroup. Okay, so that's what we do. So let X be any element of G and A be any element of K. Then we map X inverse AX, and that is, since F is a homomorphism, this is F of X inverse times F of A and F of X. But F of X inverse is inverse of Fx, F of X. And F of A, since A belongs to K, is the identity element of H. And we have this. And so this is just identity. We have this. So F of X inverse and F of X, which is H, the identity element of H. Therefore, X inverse A X is an element of K, because any element that is mapped to the identity of H belongs to K by definition. So, therefore, K is normal. And we are done. And this set K, defined by this. So if we have two groups G and H, and K is a subset of G that is mapped to the identity element of H. Okay, so F is a homomorphism from G to H. Then this K is called the kernel of F. Okay, so visually, this is something like this. So we have G and we have H. There is one special element called EH that is the identity element. So every element of G that is mapped to this particular element, so this subset is K, is the kernel of G, of H in G. Okay, so this is the kernel. So this mapping is F. So as we have seen in the theorem, the kernel of a homomorphism is a normal subgroup. By the way, we write kernel by this notation. So kernel of F is this.